Well, ladies and gentlemen, welcome back. Our next session is going to look at operations in the air and will focus on innovation in two flight operating systems. First of all, air traffic control, and then unmanned aircraft. So our next speaker, with the title Innovating Air Traffic Control, will be David Hawken, Engineering Director of Operations at NATS. And actually, I had the privilege of visiting NATS recently and really came away deeply impressed with the technology that's being deployed. So David is, as I said, the Engineering Director in Operations of what used to be known as National Air Traffic Services, now just NATS. And he's responsible for leading a team of 800 engineers who design, procure, operate and maintain the sizable engineering systems used to provide en route air traffic control in the UK. David's a chartered engineer and a fellow of the IET, and he will explain some of the innovative ways that are enabling NATS to deliver tangible improvements to safety, capacity, value and environmental impact of air traffic control. David Hawken.
I've got to say, after the last session, I am an engineer, so I have got slides. Well, in the UK, we've got two air traffic control centres, and our area of responsibility covers, it's called the Flight Information Region. So we've got one centre at Swanwick in the south coast, and that looks after broadly England and Wales. And then we've got a second centre located at Prestwick, which looks after the Scottish area and also half the North Atlantic. So we also provide air traffic control as you're flying over to the US and to Canada, and we look at halfway roughly across the North Atlantic and actually quite far down south. So when you're going to the Canary Islands, we're also covering a lot of the traffic into that area as well. We've also got air traffic control at airports. So we run the air traffic control on a commercial basis at 15 of the major airports in the UK. And because air traffic control is beginning to be deregulated across Europe, with Spain, well, the UK being first, but now Spain, we've also got contracts to run some of the Spanish airports in collaboration with FREng, where we have a joint venture with them. That's all about the air traffic, but being an engineer, I want to get onto the engineering aspects, which I personally find more interesting. So how do we do all of this? We've got, as you might expect, a wide array of sensors across the UK. So we have radars, communication stations for voice communications, and more recently data networks as well. And we have ground-based navigation aids as well. And we've kept those ground-based navigation aids, even though all the aircraft are now GPS equipped and they're satellite-based systems, because we've still got general aviation that we provide support to, and the ground-based navigation aids are still an essential part of for integrity for those rare but high consequence events like loss of satellites, solar flares, which really could have a debilitating effect. So we're still maintaining a basic ground network of navigation aids that we hope the aircraft and the pilots can still use. The last point on the slide, the flight data processing, that's really the heart of what we do, and it's the brains behind the function. And that's about getting people not just safely where they want to go, but on time, efficiently, reliably, and in a way that saves fuel as well. So fuel efficiency is more and more important to the aircraft. It's not just about delays, it's getting the right flight level, so there's engine efficiency. And I was thinking about the electric engines, thinking, I wonder what height they fly efficiently at. We might need to factor that into the future plans to make sure, because they're going to have different characteristics. What we're trying to do is to get the flexibility that we can actually handle traffic at any level, where they want to go and when they want to go, without some of the constraints we've had in the past. So what we look at, and over the last few years, we've made a conscious effort in NATS to do things differently, and a lot of it has just been about thinking a bit different. Thinking about the bigger problem rather than the narrow view that we might have had in the past with air traffic control, to actually work with our customers, what's important to them, what's driving their demand. And actually we've seen different networks of traffic, so some of the smaller airlines, or what were smaller airlines, flying smaller distances, actually, like people like Ryanair, want to maybe within 6 or 8 weeks start a new route up, and that can change our demand quite considerably. So they're very dynamic in what they do, whereas in the past we've been organising the airspace and we would take years to change the airspace. So we're looking at how can we speed up those processes, how can we be more cooperative with our customers, understanding their plans, also our suppliers as well, what they're doing. And I've got to say, my background has been software, and one of the things I always felt was we were in safety related software, so one day all those other people would learn that we do it the true way and the proper way of doing software. In actual fact, the dynamic way of the software is developed now in the commercial industry for games, for apps, for iPhones, actually has opened our ideas on how we can develop things to be more dynamic, more agile in what we do, and we're trying to learn from them now as well as trying to say that we did it properly in the first place, which actually the truth is always somewhere in the middle. One of the key measures for air traffic control is the level of delay, and that was emphasised earlier on in the talks about that's what annoys people more than anything else, not being able to take off reliably. We're quite proud of the fact that over the last 10 years, since 2004, delay used to be 40 seconds per flight, and that doesn't sound much, but it's averaged over the whole year, and last year our delay by NAT was 5.4 seconds per flight. So that's an incredible improvement over that time. And a lot of that hasn't just been due to technology and the systems that we put in place, well, that's had a good bearing. It's also about controllers working with engineers. It's been about us working with the airlines, that when we do have problems, we can actually have teleconferences very quickly, so we can have a collaborative decision making as to what we're going to do to resolve the problem so it has least effect overall. And when we do get a problem now, all the airlines are involved in the conversations, as are all the airports around the country, so we can minimise the effect for the customers and the flying public. I'm going to look at two examples of systems that we put into place, or one that is in place now and one that we're planning for early next year, that should also improve life even more. The first is a system that we called IFACs, and this is Future Air Traffic Control Tools. And we see that this is, has improved life for the air traffic controller to a very large extent. So one of the things that it does is it looks ahead for the next 18 minutes to predict where every single aircraft is going to be in a sector. If you can do that, you can give the controller information on which aircraft are going to come into conflict with each other if they carry on with the current flight plan, and actually, more importantly, what you can do about it. So we're trying to give the controllers lots of what-if options, so they can actually make minor adjustments ahead of time. They can slow aircraft down, they can make minor course corrections, so that actually the aircraft don't have to make tactical manoeuvres late in the flight, or actually increase fuel burn and increase their track miles. So we've seen that this has allowed more automating. It increases capacity in the way that by having this look ahead for 18 minutes. And you might say, why 18 minutes? 18 minutes was the best optimization between accuracy of where things are going, because you get more and more uncertainty as time goes on, versus so it needs to be useful for the controllers. And if you extend much beyond 18 minutes, the level of uncertainty starts to degrade the tool, so we felt this was the best optimization to give the controllers what they can do. The important bit is we're pushing out that time horizon, and we see that in the future that's where life is going to go in air traffic control. Instead of a controller being a tactical controller, sitting there doing the things that you've seen on the TV and always dealing with aircraft, giving urgent commands, it will all be about strategic control, deconflicting routes ahead of time, and actually we'll put that in the flight planning system so that we can get a 4D trajectory that if you follow it and everything else goes well, then actually it'll be a conflict-free route. You'll take off, you'll follow this fuel-optimized route, and you're into the cruise, and then you'll land at the other end without any delay at the airport. That's the utopia of air traffic control, not just in the UK, but first across Europe, where we're cooperating a lot with other European service providers, but then also across the world. And that's the holy grail of air traffic control for the future. The way that our IFAC system works is, if you start to think about it from an engineering point of view, it looks at the current position of the aircraft, it looks at the flight plan, where does the flight think it's going, and we can get a certain amount of data from the flight management computer now, so we look at that. Importantly, we look at the weather information, and we need accurate weather data as to what's happening now, so we understand where the winds are, how the aircraft are going to be pushed in a direction and have to compensate for that, slow down or speed up due to headwinds or tailwinds, so that we can get this accurate position in the future. and aircraft type also comes into that as to what their performance is, what their capability is, so that we can look ahead. And we can give the controllers pictures of both the horizontal and vertical positioning to allow them to deconflict the aircraft. It's been a huge success for us. Our estimates are that it's increased. We have a safety risk index, which is based on the severity and the frequency of safety incidents or losses of separation, and we estimate that we've seen a 20% improvement in our safety risk index. We've also seen fuel savings of around about £6 million a year, and that's about 10 kilotons of fuel, of fuel each year for the customers. So we've seen benefits already from that. I've got to say it was a challenge to get this in, because from an air traffic control point of view, we're traditionally very conservative with a small c, and we like to take little steps in what we're doing, whereas for this particular system we worked with some really good suppliers on to develop it, but we had to take account of the controllers, their concept of operation, everything they've been taught to do, educated with, to use paper flight strips in the past, and they were very used to using paper flight strips. Just like the engineers using PowerPoints, the flight strips were the controller's comfort blanket, and they would annotate the strips, and it's very manual, but it's actually very reliable. Paper flight strips don't turn off if the power goes, whereas the new IFAC system does away with paper flight strips. So that was a big change for the controllers, and actually needed different skill sets. So we had to train the controllers, educate them in how they were going to do that. We also had to convince ourselves first, but then the regulators, that this was a good thing to do, and that we could get the integrity, the reliability, and all the other aspects that we need to make sure that we could get the safety assurance so that we could use it and be confident about that. I've got to say now the controllers wouldn't be without it, but it did take some education, and the people change part of that we couldn't underestimate, and we've learnt a lot of lessons in how we do that for the future in terms of introducing change that affect the air traffic controllers. So this is one thing that we're really proud of. It's probably the future is we'll use this in other centres as well. It's currently in Swanwick. We'll be looking to introduce it to Prestwick in the future, and there's interest as well from other European countries as we're moving this forward, and they're doing something similar. The electronic nature of this is one of the areas that we see as a big, I say innovation, but a big improvement in air traffic control, because as soon as you don't need paper flight strips, the electronic capability allows you to do things you could never do before. One of the easiest ones that we do now is we check, when we give a clearance to an aircraft, the aircraft can put it into their flight management computer, and we can downlink what the aircraft has put in. The best thing about that now is we can compare the cleared flight level that we've told the aircraft to go to what they've actually selected in the flight management computer. And we've automated that now, so if they actually put by mistake, because either they misheard or we actually gave the wrong information, and that happens because it's transmitted verbally still in a large number of cases, we can automatically check that and then produce an alert for the controller, who can then correct the situation. And we see that's improved safety. Some of the pilots are a bit surprised that we'll tell them, actually, we didn't ask you to do that, we asked you something different, because they weren't aware that actually we can see all this information. But they've learnt themselves now that we have that oversight as well. And it's been good for everyone in the industry, I believe. The second innovation that I want to pick on today as to what we're doing is time-based separation. And this will fix a problem to do with weather resilience, which is a big cause of delay. Certainly when you come into any major airport, if there's strong headwinds, then all the aircraft coming into land slow down. However, all our air traffic control standards are to separate aircraft by 3 miles or 5 miles by distance. And it's a little bit like when you're on the motorway. The normal motorway speed is 70 miles an hour, so you'll stay a fair distance behind the car in front. And that's quite right and proper. But when there's a traffic jam, or when you start to slow down, you'll come very close to the car, or closer to the car in front. Unless you're a BMW driver, in which case you're there already. But or a white van, so I shouldn't have said BMW. What we're doing here is doing something similar for when you come into approach. If all the aircraft slow down, then actually it's safe to come closer together. There are still some constraints. We're not going to be tailgating. You'll be pleased to know with one 747 behind another. You won't be able to see the whites of their eyes or anything, but we can reduce that separation when those circumstances apply. And we see that will save approximately half of the delay that happens at Heathrow every year due to strong headwinds, and that's about 1,300 hours of delay. That's all the aircraft added together, the cumulative delay. So this should reduce that by about a factor of 2, and we see that's a massive improvement in when you come into Heathrow, and then it will be installed at Gatwick in the future is the intent, and probably other airports too. The hard part of this was first of all convincing ourselves that this was a safe thing to do. And that's probably the thing that, again, because we're conservative in nature, we have to do a lot of research to say, actually, can you do this? Conceptually, with the car option, you can think about it, but when you talk about the complexity of aircraft, there's weight vortex, which is where there's disturbance behind a leading aircraft that depends on the weight of the aircraft. We were concerned about that. How do we know the weather reliably? What if the wind changes? What are we going to do about that? Is it safe on the runway? Can we exit the runway quickly? Because once you're on the ground, you're on wheels, and so it's a slightly different situation. So we've done a lot of research with partners to actually work out what is a safe thing to do, convince ourselves, then put the systems into place, train the controllers, and we believe that by next spring we'll be ready to actually deploy that at Heathrow to improve your landing rate at Heathrow for the next year, over the future years. The other things that we're doing is, I said before that the utopia for air traffic control is a 4-dimensional clearance for aircraft that will be seamless operation across borders. Because even now, certainly within Europe, less so in other parts of the world actually, we're still very country specific in how we provide air traffic control. And that has some built-in constraints about how we do things, the interoperability of what we're doing. There's a lot of politics in this, that everybody thinks that actually we could provide air traffic control across Europe with a lot less centres, and every country agrees with that, provided it's not their centres that close. So actually there's some politics that's got to be resolved. From a technical point of view, where we can help though, is if we can aim to make it a seamless operation, so we've got consistency in the data that we're providing, we're cooperating across the air traffic control providers across Europe and beyond, then we can get the same outcome. And that's where I'm putting our effort into at the moment, to make sure we have a seamless operation. We also see that we can have improved profiles for arriving, departing aircraft. The stacks that you probably know and don't love when you used to come into Heathrow and you'd be circling for an hour, they'll still be available because there could be constraints that mean we have to have those, but our aim is to remove the need for those. And if we cooperate, we have a system called Arrival Manager, and we're looking at Extended Arrival Manager, where you start to slow down aircraft maybe 100 miles out or 200 miles out, and they'll descend on a continuous descent. That's good for fuel, it's good for the delays, so that you come in on a predictable route and then you'll just land at the airport and everything will be ready for you to move ahead. We're also looking at that function at the airport. So how can we help the airports with data and information to be more ready for when the aircraft lands? Because if you see videos of airports, it's like a ballet. The aircraft comes in, it comes to the gate, the passengers are getting off, more passengers are waiting to come on, but you've got food to go on board, you've got crew to change, you've got cleaners, there might be a bit of maintenance that's going on, some maintenance checks, and all of that has to happen in the turnaround time, which certainly for short-haul aircraft is very quick. If you've ever been on an EasyJet, Ryanair, some of the other Flybe, the other short-haul aircraft, they're really looking to turn around as quickly as they can. And if things are delayed or disrupted, it can be a knock-on effect for the rest of the day. So we're looking at, okay, how can we work better with the airports to make that a seamless operation as well, and cooperate so it makes it not just gate-to-gate seamless, but also we look at now cruise to cruise. So when the aircraft's in the cruise, how does it come down on a continuous descent? How does it get streamlined at the airport with the airport customers? And then how does it take off on a continuous climb till it gets to its next cruising altitude? And we're trying to think a little bit differently from that perspective, rather than thinking, well, it's not our problem when it's on the ground. The other area for the future is unmanned airborne vehicles. And we need to make sure that we have a way of integrating them safely with other traffic. So I think the next speaker is going to be speaking about UAVs and the challenges that presents. From an air traffic control point of view, we need to be at the heart of that as well. So we're doing some trials, we're looking at how we can help the UAV market and the users of those, so that it does integrate seamlessly, so we're not a constraint, we're an enabler to get them into what they need to do and what they want to do. And that's just not the large ones that we're talking about, it's also the small UAVs as well that present a risk to traffic, because the small sort of remote controlled aircraft that you might think of in the past getting bigger, and actually they can start to cause risks as well, so we need to manage both dimensions. I guess my closing thoughts is really about how have we gone about all of this. And some of it's about new technology and being a bit open to new technology. So the Googles of the world, the Apples of the world, what sort of approaches are they taking? What are the games market doing as well? Because actually there's some really clever people in there that are taking a different approach. And we've got younger engineers who've got different experiences and they're thinking about that rather than... So at some point in my career, I became the Luddite, the old guy. That I still think I'm 18, but actually that's not true anymore. So it's actually getting those new ideas, working with customers and what really matters to them, and actually being brave. So, you know, taking the odd bravery tablet doesn't come easily in our industry. To take some risks, not safety, and do it in a cautious way, but actually look at what we can do, spend some research money to look at the options. And take some advantage of what's there. And I've found that the ideas need nurturing and encouragement. If you don't do that, then they're never going to be successful. It's always helped when there's an imperative or a deadline, and we sort of create some of those artificially, I'll be honest, internally, to encourage things to actually move forward so that we can be progressive and actually deliver things on time and to less cost than they otherwise would take. And there has to be a drive from the senior management to deliver the outcome as well, which is where I see some of the things we can do in the room to actually drive that imperative. What I would say is, as you're next sipping, my final request of you, I guess, is when you're next sipping your gin and tonic on board, and everything's going well, so I don't mean to be cursing about us, but just have a thought for the engineers and the controllers that are behind the scenes, making sure that you're getting where you want to safely and efficiently. Thank you.
Well, thank you very much indeed, David, and we'll be hearing from you again at question time. Now we're moving on to Astrea, the key to the civil unmanned aircraft market, and it's my pleasure to introduce Lambert, Dopping-Hepenstal, and Lambert is the Programme Director, which is the UK industry-led consortium focusing on what is needed to allow autonomous vehicles to operate safely and routinely in civil airspace over the UK. Lambert has a long and distinguished career with BAE Systems and his predecessor companies. He was the systems design engineer on Hawk, Sea Harrier and Harrier 2, and managed the systems development of Tornado and Typhoon. He was elected a Fellow of the Royal Academy of Engineering in 2007, and he's going to explain to us the challenges faced by industry and the regulators in realising the opportunity to operate unmanned aircraft.
Thank you, John, and good afternoon, ladies and gentlemen. I'll just leave that up for a moment because having been to Swanwick, the thing that really struck me was there wasn't a level of panic. I'd always rather imagined air traffic control places as people scurrying around looking worried, but it was just too calm. Right, so I'm going to talk about unmanned aircraft. I mean, yet another major step in aviation. But I guess one thing that strikes me this afternoon, I mean, we've heard of a lot of really exciting, possible sort of almost revolutionary steps in aviation, which must be a huge encouragement to young people coming into the industry. I also thought I'd better just start off is I've called them unmanned aircraft here because I sort of seems an easier term, but we have a terminology problem, if you like, is that they're referred to as unmanned aircraft systems because they are systems, because you've got both aircraft and ground stations, UAVs, remotely piloted air systems, and indeed the press likes to call them drones. They're all basically the same thing. So I'm going to just look at a little bit of what are the opportunities here, why is there an interest in going unmanned, talk about some of the technical and other challenges that we face, where we've actually got to along that journey, and what we've got to do to finish off the journey and actually bring them to reality. So, I mean, what's the key? Why unmanned aircraft? Well, I think really the three sort of differentiators from manned aircraft are about size. They're completely independent of having to carry people on board, which to a large extent do have an impact on the size of aircraft, and indeed the life support systems basically an aircraft has to carry. And so they can be any size you like, from tiny ones to huge hybrid air vehicles. They can go into places that you wouldn't risk a manned aircraft. For instance, at the tsunami in Japan with the Fukushima nuclear power station, they used a small UAV to go and inspect that. I always liked the picture of the Eyjafjallajökull volcano in Iceland that disrupted European aviation for a long time. And the other thing is, again, because you're not having to carry people, their endurance can be, weeks, if you like. You don't have to bring people back down for a bit of a rest. So we're really talking about a new branch of aviation. It's not replacing the manned part of aviation really substantially. It's about other new opportunities that we see we can do with aircraft. Just touching on its origins, like most things in aerospace, it does actually have military origins. I mean, whether it be the jet engine, radar, fly-by-wire, composites, all of these things started really in the military world. And that you go back to the First World War, where they were playing with remotely piloted aircraft. Then in that period between, they were largely used as aerial targets, and hence this term drone was the term used to describe that. In the last 10-15 years, particularly pioneered by Israel and the United States, they've been used for reconnaissance and operations on the military side. But currently, I mean, they are restricted to flying in what's called segregated airspace. And so the challenge for enabling this market for non-military use, for civil use, is to get out of that constraint of segregated airspace. So, I mean, if we look at potential applications, and it's a bit like the hybrid air vehicle one in some respects, is the market will develop once we found out how to do it. And it's to some extent a limit to the imagination, but clearly things like search and rescue, I mean the MH370 loss of that, a lot of the search and rescue planes spent almost their whole time on going to the search area, whereas again you could put unmanned aircraft up sort of totally persistently for, as I say, potentially weeks to search an area. And there are a whole load of other things, and agriculture, there's a whole list of possible applications there. Already mentioned is this telecommunications, effectively sort of very low orbit satellites, if you like. But small ones are already being used for a whole load of activities, televising sport and certainly doing sort of agriculture, looking at fertilizer patterns and things like that. Estate agents have been using them to advertise their products, and archaeology. And just in the papers the other day about EasyJet even using them to inspect their aircraft as potential. So I think it's really up to your imagination as where they will go next. And so the market will develop really when we get the space accessible. So the challenge really is the regulations have been incrementally developed over the last 100 years or so, but all assume basically there's a person on board in charge of that aircraft doing some essential activities. And although the level of automation and things like that has increased, still the pilot is ultimately responsible for not running into things and for talking with the air traffic controllers and for monitoring the health and dealing with health problems on the aircraft. And so the challenge that we face is industry to develop and the users to develop this market want to know about the regulations, the regulator said, well, give us a product and we'll tell you whether it's safe or not. And so, but there are clearly technology and regulation development required to enable this. So Australia was formed in 2006 with a very simple objective: is how do we do this, and in all classes of airspace without any special restrictive or conditions of operation, and this sort of transparency and equivalence with manned aircraft. So they've got to operate in the same way, work with the air traffic control system, as David was just telling us, in the same way, and certainly be at least as safe as manned aircraft. And so Australia was formed to, as a partnership activity of really the major aerospace companies in the UK, getting together with support of the Technology Strategy Board. Well, originally it was the Department of Trade and Industry, the Welsh Government and Scottish Enterprise, and supported by a large number of smaller companies and universities, and working closely with the CAA. And to date, we've spent something over £60 million on this programme. As I say, it is a system. It's about an unmanned aircraft working in an environment obviously connected to a ground controller in some form, working with the air traffic control system, avoiding obstacles, whether other airspace users or obstacles on the ground. And so it's a systems engineering problem, and it is both technology and ways of operation, concept of operation are important. The AS at the beginning of Australia is about autonomous systems, and I guess really it's an understanding is why do we emphasise this? And the reason is that taking the pilot out of the aircraft, we've got to be able to replicate some of the tasks that the pilot had, and say, avoiding others, understanding weather and where appropriate, avoiding weather, understanding icing conditions and things like that, and certainly looking after the condition and health of the aircraft. Now that in itself, we could transmit the data down to a ground pilot. Unfortunately, that's not actually totally practical, in that there's an awful lot of data you need to transfer down to the ground, and so it's a challenge in terms of bandwidth problems in doing that practically. And for the odd one it may be okay, but if you're going to develop this into a major sort of industrial opportunity, that's not really practical. But we've also got to cater for the conditions of the loss of that ground link. We can't absolutely say that that will always be there under all circumstances. That talked about solar flares and things like that before. There are circumstances we will lose that link. And also, if the air vehicle develops faults, it may in itself have a fault and therefore needs to be able to operate safely. So we have to transfer some of that intelligence that the pilot has into the air vehicle itself. I'm always very good at forgetting major points in my notes. And a pilot sees, hears, feels on board the aircraft. A presence there. Now, autonomy is not a frightening thing. These things are not going to open the hangar doors in the morning, go off and fly themselves, and then come back, land, and close the doors afterwards. We're really talking about variable autonomy here, in which there is a dialogue with the ground pilot. If the vehicle feels that there is a potential risk of collision with another air vehicle, it will send a message down to the ground pilot asking for instructions. If the ground pilot fails to respond to that for whatever reason, then it will raise its level of autonomy, saying, well, okay, not heard from you, I'm going to take this manoeuvre in 30 seconds time unless you tell me otherwise, and then fails to get that. It will always then finally take control itself and do a safe manoeuvre to avoid a collision. So that's the concept of autonomy. What I'll briefly now is just talk about some of the sort of major programs of trying to integrate some of this stuff together is done, and some of the major areas that we've got to tackle. And so this autonomy bit and decision making is all about this mission system being able to handle this, but also if we ever get the endurance, we've got to be able to do probably some form of air-to-air refueling. Quite a complex task to do that, and so we've even been looking at things like that. Power management, if we're going to get the endurance out, we've got to be pretty frugal with our power use, and so looking at how we schedule and manage power a stage further than current aircraft do. One of the keys, as mentioned, is about this link with the ground pilot who is responsible for this aircraft, and so the human factors aspects of it. And it's quite interesting, is just like in manned aircraft, I think it's something like 80% of accidents are attributed to pilot error. Certainly in military experience in flying unmanned aircraft, the difference isn't that much greater, and therefore the getting the right information down to the ground pilot in a way that is properly accessible is really important. But also we've got to operate, as David was talking about just a moment ago, with air traffic controllers. And so how do we do this transparent way of operating with air traffic controllers? And we did a lot of simulation work using NATS controllers to try and understand particularly the issues of latency, because you're now got a circular path round because the pilot's not on the aircraft, and there is a delay introduced with that. And that culminated in a whole series of flights between northwest England and the Inverness in the north of Scotland, working with NATS using a surrogate aircraft. It had pilots on board for safety reasons, but it was being flown by a ground pilot up through the various classes of airspace, and particularly there were, I think, 3 air traffic control sector handovers during this, and quite a lot of regular air traffic controllers were used in this. It did demonstrate transparency is possible. Now, admittedly, we did this at a period of relatively low traffic density, and all our simulations show at very high traffic density this delay does become a problem and something that needs to be addressed. Communications is pretty vital in this game, because you've now got a new communication link. You know, normal aircraft has the air traffic control link. You've now got this so-called command and control link to the aircraft, and so that not only needs very high integrity, but it also needs to be very secure. And so that's part of the challenges we're doing. But as I mentioned about the bandwidth of information coming down, is that because you're going to wanting to fly these things large distances, you're going to go beyond beyond radio line of sight of the aircraft. And so in order to get an affordable system with not a huge amount of infrastructure, and although one solution is to use satellite communications, that is expensive, and that will further limit bandwidth availability. And so we've had to look at other possible ways, and one system that looks very promising is ad hoc networking, in using all the flying vehicles, and again David demonstrated how many there are up there. If you could borrow their radio systems as ad hoc relays, then you could have a very efficient and very available system there. And so that's something we've been looking at, but security is going to be quite an interesting issue. What everyone tends to talk about is the detect and avoid, replacing the pilot's eyes, and so we've done again a load of simulation work, and in fact, I mean, interesting listening about your IFAC system from the previous talk. One could see that maybe some form of integration of that into the unmanned aircraft might be quite a powerful system to us as yet another assistance in that role. And so again, huge amount of simulation, an awful lot of aircraft work using surrogate aircraft doing data collection, And again, flight trials, and this is an example of flight trials. These pink flashes are false alarms, and these will have to get filtered out. But I mean, here's an example. This happens to be a Typhoon aircraft that was going across the thing, so a very fast-moving, high-speed target. But you've got to be able to see this against all sorts of different backgrounds. Now, the expert in the system is going to be downstairs at the drinks break at the end of the day with some of the equipment and so you can talk to Rod in a lot more detail about how these systems work. One of the other things I talked about the importance of developing the regulations. Now, we're not going to have a whole set of new regulations for unmanned aircraft because, again, that goes away from the transparency thing. We really need to put some annexes, as it were, onto existing regulations. One very innovative idea that the project came up with was what we now call virtual certification, of trying to understand, you know, everyone says, well, you've got to do a sense and avoid system, but what else have you got to do? And how do you make sure you've covered all the bases that are needed? And so we took an actually quite boring but very well understood aircraft, a Jetstream 31, in which we had all the certification material for. We imposed on it our unmanned aircraft architecture, a set of concept of operations, the technologies that we've been developing under the Australia program, and then laboriously went through the whole set of certification documents, photocopied the ones like the undercarriage, which are completely transparent as to whether it's unmanned or not, modified the ones like maybe the flight control system that will need some adaptation but still has many of the attributes of a manned aircraft, and added new pages for things like the detect and avoid system and the command and control link, which are not present on manned aircraft, and dumped this vast pile of paperwork on the CAA, who then went through this lot to give not a clearance, as it were, but advice as to, yes, does that stack up or not? And both ourselves, industry, and the CAA have learned a tremendous amount for going through this process of really trying to discover some of the unknowns in the process. So we're much more confident now. We understand all of the things that we really do need to address. And, you know, a pretty unique approach. And I think one that's probably applicable in lots of other fields, maybe in medicine, maybe in, you know, other transport areas. So that's where we've got to at the moment. We're around the technology readiness level for most of the technologies of around 5 or 6. We just started with the support of the Aerospace Technology Institute that was spoken about right at the beginning, the first next step. And we've imposed this on the European roadmap. There is now a European and a US roadmap for developing unmanned aircraft in a progressive form, and as you see, it goes out to certainly towards the end of the next decade. And so Australia 3A is a fairly small program of over 18 months, looking, really continuing to work with the regulators, further taking the virtual certification process and standards organisations. And then we're currently in the process of putting together a bid into the ATI for a much bigger demonstration program that is looking to really verify and validate all these programs, and most particularly really trying to get the UK, which is in a strong position here. The CAA are very highly regarded in the work that they've done, and the UK is one of the few areas in which small unmanned aircraft, that's ones below 20 kilograms, can be licensed to fly for aerial work. But they are very restricted conditions. They've got to be in direct line of sight of the pilot, within 500 metres of the pilot, below 400 feet, so they can't possibly interfere with other aircraft, and no closer than 50 metres to a structure or a person. But at least the market is developing, and there are some 200 operators licensed in the UK, and many other countries are now beginning to follow the UK example here. But this is about taking the next big step to letting the lead off these small ones and allowing much larger ones to fly and do some real serious work. So the challenge is, well, it's a highly regulated environment that we are operating in, but that's probably a good thing. It's much easier to do it in the air than on the ground, and so, you know, autonomous cars are a much bigger challenge than autonomous aircraft. We need international standardization because we don't just want to be constrained within our own borders. Public perception is a very interesting challenge, and in fact on the right there is some work that the Academy did on autonomous systems a couple of years ago, looking at the social, legal and ethical issues around autonomous systems. And you know, the public did really, helped by the press, talk about killer drones and spies in the sky. I mean, that has tended to ease a bit now as people do see that there's some real advantage from this, but we've got a lot of work to do to carry the public with us to see the real advantages of here. And I think, you know, that certainly some of the regulatory processes we're developing and some of the technologies will have applications in other sectors as well. So that very rapidly is where Australia's got to and where it's going next. I guess the real strapline is safe to fly and flown safely. So if you want to find out more, one of the experts on the programme will be downstairs at the end of today. And in fact, in the Royal Academy's publication Ingenia, which comes out in the middle of June, there is an article on the programme as well. So a quick trail for that, yes.
Very well done. Thank you very much. Now we're ready to take questions, and I can't believe there won't be a host of questions in this particular area. So who would like to start off? Yes, yes, sir.
Since World War II, the responsibility for safety of an aircraft seems to have been fairly evenly split, despite what is alleged, between the pilot and the ground controller. By and large, this has worked, with one or two exceptions. And I suggest that one of the reasons the pilot has a vested interest in staying alive. Once we get onto unmanned aircraft, where there may no longer be line-of-sight radio communication between the controller of the UAV and the radar people, there seems to be much more risk involved for other pilots that are up there. This concept of split responsibility is one that worries me. Is there any possibility of something like ADS-B being introduced into European airspace, which puts more information in the hands of the pilot?
So I can talk about ADS-B. So I mean, ADS-B is there's quite a few initiatives to use ADS-B and also a variant of that wide area multilateration. We use that in the North Sea area and some of the oil rig areas already. There's also proposals to have satellite-based ADS-B, and that's been in the news recently, and there's companies that are looking at that. I think ADS-B will be the future, or some variant of that, ADS-C as well, as the next. We don't imagine that we will be replacing all our radars with the same radars that we've got at the moment with the turning gear, and data link and being able to downlink parameters is the future of where we need to be for that strategic control. I'm not sure if that fixes all the problems that you're suggesting about responsibility and personal responsibility. That's a slightly different question.
Yes, certainly part of the trials on Australia looks at using ADS-B as one of the aids to separation and collision avoidance. And again, Rod can explain afterwards in some detail the work that's been done there. But I guess it's unrealistic to think that all parachutists and glider pilots and things like that will be ADS-B equipped certainly in the near term. Although, I mean, there have been suggestions that, mandating equipment like this is one solution, but we see it as a pretty heavy-handed solution, and would delay, the market developing. And so, what we've got to do is find decent alternatives, and hence these sort of vision-based systems that, using off-the-shelf cameras again that you can see downstairs, does look very promising at giving a good good results, and certainly the pilots that have been doing these trials, because these have all been done in surrogate aircraft, their comment has been, if I know where to look for the target, because the air traffic controller has said, there's an aircraft going there, then I see it at about the same time that the system does. If I don't know there's something out there, the system sees it first. And so I think we more see this is actually going to be an aid to general aviation pilots, and so we can see a market actually in general, because after all, this isn't going to replace general aviation pilots, because you do it because you enjoy flying. And so I don't think you'll have nearly as much fun if you're sat on the ground controlling your aircraft. So I think we see these technologies being spun out really more as aids to other flyers as well, because they will enhance the safety. And I think most of the technologies we're developing will go into manned aircraft to potentially improve the safety, potentially improve efficiency, and the security of aircraft.
Simon Jones from Journey 2100. I want to ask you about the MH370. It's inconceivable that can actually happen in this modern day and era. Am I right in saying also that when the planes go from America to Europe, I think we still lose them for about several hours, communication with the air traffic control. So does NAT have something, let's say, that maybe the Malaysians didn't, or how can we stop that happening in the future? As sort of belts and braces, because I've always seen the aviation sector as having double and triple systems, especially in the cockpit. So can you just give a bit of commentary on the future of that type of thing not happening, and spreading your best practices? Let's say you have technology at Heathrow that maybe the rest of the world doesn't, or you can,
I think over land masses, surveillance, which is a more general term for radar, is relatively easy because we have radars in the UK. We have effectively total cover for the UK in terms of radar coverage, as would the whole of Europe and the Far East. There's other military radars or civilian radars. There's primary radar that just bounces off the aircraft, so you don't need any cooperation from the aircraft, or the secondary surveillance radar. On the North Atlantic, like any other large ocean, there is no place to put radars. So the technology has been different. It's been done procedurally historically. Over the North Atlantic, we get position reports from the aircraft, and we get more regular position reports, so that we have more recent projections of where they are, and we understand what their intent is. So we understand their four-dimensional clearance as to where they're going. There's also the North Atlantic is also a busy area, so there's other aircraft that are aware of the other aircraft around them. So there's a sort of built-in better mechanism for actually knowing which aircraft we've got, detecting when they're deviating from their clearance, and then we can do something about it if it's search and rescue at the extreme. So we're also looking at the North Atlantic for the future, working with our Canadian partners who look at the other side of the North Atlantic for our part of it, looking at the future to put ADS-B in, satellite-based ADS-B as sensors, so we'd have very frequent reporting of where the aircraft are. And that's what we expect for the future. And some of the satellite-based ADS-B would actually give global coverage. So whether people are subscribing to it is a separate aspect. Plus, Inmarsat have made an offer that they will detect where the aircraft are. They tend to log on to where the aircraft systems are for maintenance, and that's actually how that aircraft was detected to some extent. It wasn't subscribing to the Inmarsat service at the time, is my understanding, although I'm not an expert in that. But that's how Inmarsat were able to track where that aircraft was to a lesser accuracy.
Lambert, anything you would?
Well, I guess again this ad hoc networking communication system that we've been looking at, you could see that giving a highly redundant sort of communication set in most areas, I think, so would supplement, satellite coverage as well. So I'm sure there are things that can be done.
Yes. Did you try the simulation of emergency landing or procedure when the engine fail or system fail, and what will be possibility for the automated system to make a decision without the human?
Yeah, and I guess in some respects there is an advantage with an unmanned aircraft. One is that you can do manoeuvres that are not necessarily possible or desirable in a manned aircraft because you've not got a person on the aircraft. Your navigation system will have mapped all potential landing sites, all the fields, all the village ponds, etc., as it were, that's there. And we've done some work using, for instance, infrared cameras so that you can then check that this field hasn't actually suddenly got populated with the local scout troop having a camp or something, which would therefore render it not a safe place to land. And so I think because you've got all this data on board, again, I think it's probably something that could enhance the safety of manned aircraft rather than being actually a disadvantage to unmanned aircraft.
I'd ask you all to show your appreciation for David and Lambert.